you guys all in class. This video is going to go over section 6.6. Yeah, 6.6. We're going to use proportionality theorems. So let's go ahead and get started so we can get through this lesson. I'm going to go ahead and share my notes here. Here we go. All right, so 6.6 has a lot of theorems. We haven't had a lot of theorems up to this point. We just had the few that dealt with similarity, and we're still kind of talking about similarity, but we're talking about some special cases with similarity. So let's go ahead and jump in and kind of get started. So we have 4 theorems that we're going to talk about today. We're really going to focus on, whoops, not that way. Let's start here. We'll just make it really big here. How's that? So what I want to talk to you about is what happens if you have a triangle. So here's my triangle QRS, and you draw another line that is parallel to QS, and we're going to call it TU. So you draw another line parallel to that. What happens? Is there any special relationships that happen when you draw this line TU? And so there actually is, because obviously you can see that we have a theorem, and it's called Theorem 6.5, the triangle proportionality theorem. So if a line parallel to one side of a triangle intersects the other 2 sides, then it divides the 2 sides. And our word, this section is not congruent, but they divide the 2 sides proportionally. Okay, so I think this is pretty easy to see. Okay, so basically what's going on is you have one side here, QS, that's your side of your triangle, and then you draw a line parallel to that, which is TU. All right, so it says if TU is parallel to QS, then, and then here's the kind of interesting part. If you go from R to T, and you put that in a ratio from R to T with T to Q, that equals the same ratio as from R to U over U to S. Okay, so basically if I wanted to color code this, it would be R to T here, right? R to T over T to Q, so that section there, equals R to U over U to S, right here. Wow, we look like a preschool going on here, right? All right, so that's what's going on with that theorem. I think it kind of makes sense with what you've seen so far. Like, it feels like something that should be right? If those 2 lines are parallel, then they should divide the other 2 sides of the triangle into two proportional lengths. I'm just double checking something here. All right, yep, we're good. All right, so it should work out. Like that feels like something that should work, right? All right, so that's the first theorem that I want to talk to you about. And then the second theorem is the converse of the triangle proportionality theorem. So this one says, not surprisingly, if a line divides 2 sides of a triangle proportionally, then it is parallel to the third side. So this is a converse theorem. Remember, it's when we switch the hypothesis and conclusion. I can talk today. So we're basically taking what I just did up here, and you can see here we're flipping the hypothesis and conclusion. So if RT divided by TQ is equal to RU divided by US, this is the proportionality part, right? I won't make you watch me write proportionality. This is the proportionality part. If those 2 are proportional to each other, then you can assume that TU is parallel to QS, right? So theorem 6.4 is if those 2 lines are parallel, then the segments that it divides into are proportional to each other. 6.5 is the opposite. If the segments that divide 2 lines are proportional, then those 2 lines are parallel. The 2 third sides are parallel to each other. So I think it makes sense, pretty straightforward. Let's do a couple quick examples with that. So example number 1 says, in the diagram, QS is parallel to UT. So they're already telling me that things are parallel, so I know that I'm going to use 6.4 because that tells me some information, right? And then it says if R to Q is 10 and R to S is 12 and S to T is 6, what is the length of Q to U? So I want to figure out what is the length of Q to U. All right, so we just learned this theorem, right, where it's just a straight application of the theorem that we just learned. We know if these two lines are parallel to each other, that the two lines that it divides out to are then proportional. So R to Q over Q to U has to equal R to S over S to T. So R to Q is here, over Q to U here has to equal R to S over here over S to T. So just make sure that you got this. It's like you're comparing all of one side to all of the other side. It's a little bit different than we've done some of our comparing proportionality. So you're comparing all of one side, that's one ratio, to all of the other side, that's the other ratio. Okay, so then once you set that up, then we're just going to fill in the blanks, right? R to Q is 10, Q to U is X, we don't know what that is, R to S is 12, and S to T is 6. So we can go ahead and cross multiply. A lot of times before I cross multiply, I like to simplify if I can. So this is 10 over X equals 2 over 1. 12 over 6 is 2 over 1. You don't have to do that, but it just makes your life easier. You might even be able to tell that X equals 5 just by this proportion, right? But in case not, 2X equals 10 or X equals 5. All right, and that kind of makes sense. Like, look at my picture here, right? If this is 12 and then this is 6, it's about half. Then this is 10 and that's 5, that's also half. So proportionally, it makes sense. So that's how we would use theorem 6.4. So then let's, of course, slide over here and slide up. And in this picture, we want to know, is QT parallel to RS? Well, based off of this picture, I would say no, right? But we can't ever always base everything off the picture. So we want to know, is this line segment, is this parallel to this line segment? Again, they don't look very parallel, but if they are parallel, then P to Q, I'm looking at the top, P to Q, right, divided by Q to R. So this segment compared to this segment would have to be in the same ratio as P to T over T to S, P to T over T to S. All right, those two ratios would have to equal each other. The side ratios would have to equal each other. So we can just check this out by putting the numbers in, right? And that will help us out. So P to Q is 18 and Q to R is 38 and P to T is 36 and T to S is 80. All right, so I got to do some simplification here. Let's see here. Oh, well, I don't necessarily have to simplify. Actually, what I did before also makes sense. So what we can do is we could cross multiply and see if they actually equal each other, right? Does 18 times 80 equal 36 times 38? So 18 times 80 is 1,440, and 36 times 38 is 1,368. So these do not match. So therefore, we can we determine if QT is parallel to RS? No, not parallel, right? Based off of our picture, we already kind of suspected that, but you know, we had to double check it. So that's how you'd use the two theorems. Nothing too crazy or difficult with that. Just make sure you're comparing one side to the other side. Okay, so that's the first two theorems. But if you're in class, I would say, but wait, there's more, right? Make sure you get those theorems into your theorem sheet because you can use that on the test. So those are the first two theorems that we're going to learn today. And then the last two theorems, actually, I think these are the last two theorems of the year, right? We can say that because I won't, you know, this is kind of our last material. So there we go, our last two theorems of the year. Oh, I can't really get that one on there. Okay, there we go. All right, so the last two theorems that we're going to talk about are theorem 6.6 and 6.7. They have no names, just no name theorems. These also kind of play off the same thing. So we've got theorem 6.6, and it says, if three parallel lines intersect two transversals, then they divide the transversals, and our word, again, is not congruent. They divide the transversals proportionally. They divide them proportionally. Okay, so here are your parallel lines. You've got UV, WX, and YZ. Those are your three parallel lines, and L and M are your transversals, right? So if you have two transversals, and they then divide the transversals proportionally. So UW over WY, okay, equals VX over XZ. Vx over xc. So again, this kind of actually reminds me of those two theorems that we just learned. It just, in the other two theorems, it was a triangle, right? And so they met at a point down here. Instead, we've got three lines that are cut by a transversal. So again, it's the proportion of the top line, the top transversal, to the proportion of the bottom transversal. Those are proportional to each other. Okay, and so we'll do kind of an example with that. And then the last theorem, right, actually kind of comes in out of nowhere, and it says, if a ray bisects an angle of a triangle, so this is ray CD, right, and it's bisecting triangle ACB. It's bisecting because these two are congruent to each other. That's what bisects means, right? If a ray bisects an angle of a triangle, then it divides the opposite side into segments whose lengths are blank to the lengths of the two other sides. So again, not congruent. Our fill-in of the day is proportional, whose lengths are proportional to the lengths of the two other sides. So this one's a little bit different, so I am going to color code this one. So you've got AD right here, over DB. So I feel like this one's the trickiest one to kind of get the right segments. AD over DB equals, okay, equals AC over, what color didn't I use yet? I didn't use pink. There we go. AC over BC. So this is the only one that feels a little weird for me, and I don't know if it feels a little weird for you. Like, a lot of people want to do AD over AC equals DB over BC, because it's like comparing the two sides. Now, technically, those will work, because what you're just doing is you're switching the two means, right? When you do that, you're just switching the two means. So it still will actually work that way. But the official theorem actually has comparing this side that has been cut by the bisector to the two other legs of the triangle. So again, it will work if you flip it the other way, but because of the properties of proportions, right, when we can flip the means, but technically the theorem works this way. So it's kind of cool that that has that relationship. So let's do two examples with this. So if you guys were in class, I would have to pick somebody to be the farmer. So think of somebody in your family who's the farmer, who would be funny to be a farmer. And that farmer's land is divided by a newly constructed interstate. So here's Farmer Joe or Josephine, depending on who your farmer is. I don't know why that's a farmer hat. All right, here's my farmer. And they came in and they built this big interstate right down the center of my farm. Right, here's the interstate. All right, hopefully Farmer Joe or Josephine got a lot of money for that. All right, they built this new interstate. The distances are shown in meters. Find the distance between the northern border and the southern border of the farmer's land. Okay, so the farmer's land is this area here. Oh, I just colored over one of my numbers. Okay, so here's the farmer's land. Okay, and we want to know what is the distance between the northern border and the southern border of the farmer's land. Okay, so what you'll notice is going on here is that the northern border of the farmer's land, the southern border, and the interstate are all parallel to each other. So we've got three parallel lines, the north border, the south border, and the interstate, and they're cut by two transversals. Okay, we've got a transversal on the west and one on the east. I don't know, the eastern land is like slidey sideways, right? So basically what we have to figure out is We know the distance from the north border to the interstate on the west, and we know the distance from the north border to the interstate on the east, and we know the distance from the interstate to the south border on the east, and we don't know on the west over here. So we got to figure out what is that distance so that we can find the whole distance. So now when I set that up, I realize, this is something that should be in a proportion thanks to theorem 6.6, even though it says it up here. Thanks to 6.6, we got 3 parallel lines that are cut by 2 transversals. So that means the sides should be proportional that are divided. So basically, if I'm going to write this out, the distance from A to B compared to B to C, right, that ratio should be equal to the distance from F to E over E to D, right? A to C is one transversal, F to D is the other, and we've got our parallel lines. So because they're cut by a transversal, theorem 6.6, we can use this relationship, right? So then we just got to fill in our numbers. So from A to B is 2,000 meters. We're in meters. I don't know. The farmer is in Canada because we're using meters, right? B to C is what we're trying to figure out. Okay. On my eastern border over here, I kind of covered it up, but from F to E is 2,500 meters, and from E to D is 3,000 meters. All right, so voila, now I have a proportion that I can solve, right? I cross multiply and I get some really big numbers. 2,500x equals 2,000 times 3,000. That's a really big number, right? 2,000 times 3,000. So if you do the math, divide both sides by 2,500, you end up with x equals 4,400 meters. I'm going to do the math just to make sure. Bust out my calculator here. You guys can do it too really quick. Just make sure. Because I feel like that's the right number, but sometimes you just, I'm like, okay. 2,000 times 3,000 divided by 2,500. Yeah, 2,400. That seemed a little weird. Seemed a little bit big. I know what I did. I was looking at the wrong number. When you cross multiply, you do get 2,400. Felt a little bit weird. But the question was, what is the distance between the north border and the south border of the farmer's land? That's where we get the 4,400 meters. That's what I get when I glance over at my work and don't trust myself. There we go. So the total distance is 2,000 plus 2,400. So Farmer Joe or Josephine owns 4,400 meters on their western border of their land. So, that'll come in handy anytime you've got your farmer cousin in town and you need to help them calculate distances from their interstate, right? All right, so bye, Farmer Joe. We got one more problem to do, and that's up here. Oh, maybe 2, maybe 1. We'll see. I think just 1. All right. This is a good one. So let's make sure that we know how to do this one. So, not shockingly, we are going to practice theorem 6.7 because it says use theorem 6.7, right? In the diagram, angle DEG is congruent to angle GEF. So these two angles are congruent. And I'm like, this is an angle that has been, this EG is a bisector of DEF, right? And that's theorem 6.7. It's kind of unique so that we know it's a little bit different, right? Use the given side lengths to find the length of DG. Okay, so we've got some things labeled on here. We know the total length of DF is 14. The length from D to G is X, which we're trying to find, and we've got this side lengths over here. Excuse me. So if we were going to use the theorem as it's stated, we would know then that DG over GF equals DE over EF. So DG is here, GF is here, DE is up here, and EF is over here. So again, a little bit different in the way we write the theorem. Some people do write it opposite, but technically that's the theorem, so we're going to stick with it, okay? All right, so let's start filling in what we know. We know that d to g is x, okay? Oh, what about g to f? We don't know what that is. We know the whole thing is 14 though, so another way that we could think about g to f is we could write this as 14 minus x. Does that make sense? If the whole thing's 14 and d to g is x, then g to f would be 14 minus x. So we've got x over 14 minus x equals d to e, which is 8, over e to f, which is 12. Okay, so now we have a proportion we can solve, and I'm going to take my proportion up here so I have a little more room. So I'm going to cross multiply, and I'll get 12x equals 8 times 14 minus x. Don't forget to keep the 14 minus x in parentheses, right? Then you get to use my favorite property, the distributive property, right? Who doesn't want to do that? So 12x, 8 times 14 is 112 minus 8x. That's what happens when I distribute my x, right? I'm going to add x to both sides, so I get 20x equals 112. Oh no, what's happening? We're not going to get a perfect number. Divide both sides by 20. And we end up with x equals 5.6. X equals 5.6. Okay, so then if I want to figure out what is the length of DG, DG is x, so D to G would be 5.6. And then if you really wanted to know what G to F is, G to F would be 14 minus 5.6, so 8.4, I think. Seem right? Yeah, 8.4. So GF is 8.4. So not a perfect number, but pretty close, right? So that's how you would use theorem 6.7. I think that should be enough to get you guys started. If anybody has any questions at any time, though, please feel free to email me, send me a message. I'm happy to FaceTime or pop on or whatever to help you out. So take care, everybody, and I'll talk to you soon. Bye.